Hi everyone. Yeah, this is Dr. H. Venkateswarlu, Professor of EC at IARE Hyderabad. Yeah, today we will be discussing about DFT. The DFT, the discrete Fourier transform. Here under introduction of this DFT, discrete Fourier transform, where uh, DFT is the transform of finite duration sequence, where DFT, discrete Fourier transform, is a finite duration sequence. Okay, so here, yeah, where DFT, discrete Fourier transform, corresponds to samples equally spaced in frequency. This is the major agenda. We will observe this DFT, discrete Fourier transform, corresponds to the samples equally spaced in the frequency of the DTFT, discrete Fourier transform of the signal. Okay, so the DFT is a sequence rather than a function of the continuous variable, that omega. Here, from this, we have to analyze that all CTS, continuous time signal, and discrete time signal. Okay, with reference to this, all are they were discrete Fourier transform, the transform of the finite duration sequence. Here we know that all where x of n, where x of t, or maybe here in this case where x of n, where this. Okay, so the DFT, discrete Fourier transform, corresponds to samples equally spaced in the frequency of the discrete time Fourier transform, DTFT of the signal. Yeah, the DFT is a sequence rather than the function of the continuous variable omega. Okay, so the derivation and interpretation of discrete Fourier transform is based on relationship between periodic sequence. You know that all are familiar with this periodic sequence and finite length sequences. Okay, so the Fourier series representation of the periodic sequence corresponds to the discrete Fourier transform of the finite length sequence. Okay, so here it is assigned that where in this case representation of the periodic sequence, the discrete Fourier series given a periodic sequence x of n with period capital N, so that x of n is equal to x of n plus r into n. Okay, the Fourier series representation can be written as where x of n, x of n is equal to 1 by capital N, the summation, where x of k into e power j 2 pi by capital N into k. So here this case, that n value, it is based on the n value. Say for example that capital N is equal to where it is 8 or 4 or whatever it is. That time we have to substitute that k equal to where k is equal to 0, 1, 2, 3, 4, 5, 6 and 7. That means 0 to 7, 8. Where n is also same, where n is equal to, right, to substitute that n is equal to 0, 1, 2, 3 and so on. Okay, so Fourier series representation of the continuous time period signals require infinitely many complex exponentials used in these all cases. So for discrete time periodic signals, e power j 2 pi by 2n of k plus m into n power n is equal to e power j, e power j 2 pi by capital N into kn. Okay, so Like this, the k value ready to substitute k equal to 0, 1, 2, 3 up to n minus 1. Here it is assigned the n is 8 n minus 1. That means here it is okay up to 1, 2, 3, 4, 5, 6, 7, 8. But n minus 1 no. So here it is up to 6. Okay. So like this we have to substitute that where k equal to where since that k equal to 0, 1, 2 to capital N minus 1. Like this we have to use this. These are the representation of periodic sequence. The discrete Fourier series is like this. For Fourier series representation of x of n, we know that where x of n is equal to 1 by n, the summation k, x of k into e power j 2 pi, here it is 2 pi capital N into kn. Okay, so due to this periodicity, we only need n complex exponentials. Okay, like this. After that, it is we are to verify that x of n is equal to 1 by n, the summation k equal to 0 to n minus 1 x of k into e power j 2 pi by capital N into kn. This is nothing the Fourier series representation of the periodic sequence x of n. Now come to the discrete Fourier series pair. We know the Fourier series is what you call x of n is equal to 1 by n, the summation k equal to 0 to that k equal to 0 to what you call k equal to that k equal to 0 to n minus 1 into x of k e power j 2 pi by capital N into kn. To obtain this Fourier series coefficients, we multiply both sides by e power j 2 pi, that is here e power minus j 2 pi by capital N into what you call r into n. For 0 less than or equal to n, less than or equal to n minus 1, and then sum both the sides, we obtain the summation n is equal to 0 to n minus 1 x of n into e power minus j 2 pi by capital N into r into n. It is also equivalence to that n is equal to 0 to n minus 1 by n, the summation k equal to 0 to n minus 1 x of k into e power j 2 pi by capital N k minus r into n. Okay, so we are to verify that where summation k equal to 0 to n minus 1 x of k, summation n equal to 0 to n minus 1 by n e power j 2 pi by capital N k minus r into n. Okay, now the discrete pair is gone using this all m as an integer or k minus r or m into n or 0, otherwise orthogonality of the complex exponential. So here it is somewhat after using this all representation of the periodic sequence, the discrete Fourier series is appeared with a periodic sequence with the period capital N, where that x of n is equal to x of n plus nr r into n for any integer r, because of that what do you call x of n, where x of n is equal to x of n, that x of n plus r into capital N. Okay, like this the discrete Fourier series is somewhat we have to verify that synthesis equation, and after that the coefficients, so we can consider this is the analysis equation. The coefficients will be calculated, measured, where x of k is equal to the summation n is equal to 0 to n minus 1 x of n and e power j 2 pi by capital N into kn. Okay, with this synthesis equation and analysis equation, so based on this DFS, the discrete Fourier series, we have to represent the periodic sequence, the discrete Fourier series, where x of k, the sequence x of k is periodic with period n. The time we are gone using the x equal to 0, how it is varies, x of here it is, where k equal to 0, 1, 2, 3 up to n minus 1. Like this, go on substituting here 0, what happens? So where k equal to 1, k equal to 2, where k equal to 3, and k equal to 4, and so on up to n minus 1. It is also where x of k is equal to x of n, x of 1 is equal to x of n plus 1, and so on. Okay, so x of k plus n is equal to the summation n is equal to 0 to n minus 1 into x of n into e power minus j 2 pi by n of k plus n into n. So like this, the sequence x of k is periodic with period capital N. So where x of k plus n is equal to the summation n is equal to 0 to 0 to n minus 1, x of n into e power j minus j 2 pi by capital N into kn. If this, the product of this, e power minus j 2 pi into n, it is nothing but x of k, where x of k is nothing but what you call, it is our DFT, discrete Fourier transform. Okay. Now the discrete Fourier series, if it is analysis equation, we have to consider that an analysis equation. We have to use that Friedel factor. We know that all are familiar with this Friedel factor, Wn is equal to e power minus j 2 pi by n. This is going to be analysis equation, and synthesis equation is followed by where x of n. So where analysis equation is x of k, and where that x of k is equal to the summation where n is equal to 0 to capital N minus 1, x of n into the Friedel factor W n k n. With this, so ready to measure that synthesis equation is ready to observe. This is all another synthesis equation where that is going to be our x of n. It is nothing but, this is all nothing but what you call discrete Fourier transform, where this case, this is nothing but a inverse discrete Fourier transform. Okay, now where x of n applied with the DFS, x of k, okay, is the periodic, so discrete, like this discrete. The discrete is like dt of t, discrete time Fourier transform. The periodic. Okay, now it is discrete, so period to discrete. Okay, like this, this is the discrete periodic, okay, like this, this all are we have seen in previous slides. With reference to this, all are discrete Fourier transform. This problem you will see that how it is varies, that Friedel factor and so on. Okay, so here this property is also somewhat involved here. The properties of duality is required, so we have to analyze the DFTs and properties of what do you call, according to duality and interchanging, how it is varies. This all we know that. With reference to this, all are what you call properties, periodic convolution, major difference between the periodic convolution and periodic convolution. Okay, so that is the periodic convolution is ready to assign this, where the summation, where the particular summation where small m is equal to minus infinity to plus infinity. Okay, x of infinity, x of x1 of m into x2 of n minus m. Okay, like this, the major difference between periodic convolution and aperiodic convolution, like this, the sum is over the finite interval. The finite interval is assigned where it is, that interval is specified 0 less than or equal to small m less than or equal to capital N minus 1. Okay, so now go on applying this all periodic convolution with the summation. Okay, the summation where the small m is equal to, capital N minus 1. Okay, where x1 of n, x1 of m, x2 of, where x2 of n minus m. Okay, and with this, after applying this DFS, discrete Fourier series, where try to verify that now it is affected the periodic convolution x1 of k, it is going to be your DFT, discrete Fourier transform, with this x2 of k, Okay, after this is the major difference between periodic convolution and aperiodic convolution. The sum is over the finite interval. We have to substitute the value of the interval 0 less than or equal to m minus 1. Repeat periodically for m outside of the interval. Okay, so after that, sometimes we require the one more property, duality. Yeah, using this all duality. Okay, so here the duality is based on that, where if it is x3 of n is equal to x1, where here it is so where x1 of n and x2 of n, after applying this, where if it is DFS, x3 of k is equal to 1 by n into summation, so L equal to 0 to n minus 1, x1 of L and x2 of k2 minus L. Okay, this is the periodic convolution example. Okay, so using this simple example graphically we write on analyze, so that we will ready to do. The Fourier transform of discrete time periodic signal. The periodic, once we are identifying that DFT, discrete Fourier transform, how it is affected with the discrete time Fourier transform. The Fourier transform of the discrete time periodic signal, the periodic sequences are either absolutely summable or maybe square summable, where x of n is equal to 1 for all n. Okay, x of n is equal to e power j omega 0 n. Okay, where x of n is equal to the summation k into ak into e power j omega k into n. So here, hence that don't have any strict Fourier transform DTFT. So we have to follow this all. After applying this all Fourier transform, okay, so we have to verify that all x of n values like this, where Fourier transform of this x of n, where x of n, here it is x of n, that x of n is equal to 1 for all n, where x of n is equal to e power j omega naught n, and so on, where x of n is equal to the summation k into ak into e power j omega kn. Like this, the periodic sequence are neither absolutely summable or square summable. Hence, they don't have any strict Fourier transform like DTFT. Okay, so the Fourier transform of periodic signal we can represent periodic signal as sum of complex exponential DFS. So in a DFS, discrete Fourier transform can be incorporated within the framework of DTFT. It is what do you call, after applying this x of n with this, where x of n is equal to 1 by, it is nothing but what do you call, we know that x of k, where x of k is DFT. Okay, it is the inverse DFT. X of n is equal to 1 by capital N, the summation. So what do you call that, where k equal to 0 to n minus 1. Okay, that x of k into what do you call, e power j 2 pi by capital N into what do you call that, k into n. Okay, like this, that x of, here the DFT versus and the IDFT. So here also we have to verify that DTFT and IDFT, we have a lot of properties using the DFT and IDFTs. We have to verify that where x of n is applicable with x of e j omega, that x of e power j omega into x of n. Okay, with the help of these all properties, we have to verify that proof based on each and every statement of what do you call that proof. What do you call that? That is properties, different properties variation. Here that if it is periodic, ak into is equal to x of k by capital N, where omega k is equal to 2 pi by k by capital N. So after that, we have to verify that the summation x of n is equal to summation k into a k e power j omega n. Okay, this is all nothing but periodic. Okay, so this is the periodic. Based on this periodic, x of n is ready to apply with ak value, where ak is the x of k by capital N. Omega k is equal to 2 pi into k by what do you call capital N. Okay, next this all equal to that x of n with after applying the Fourier transform. So somewhat it is what do you call, so the proof is involved with x of e power j omega. Okay, like this. So it is appeared. Previously it is like this. After using this x of n into x of e power j omega. Okay, so the Fourier transform the periodic signal is like this. Okay, this all are in depth of this all are go on using this r value is substituted, where r is equal to here initially minus 1, minus 2, minus 1, and what you call 0, 1, 2, 3, and so on. So the time the k value, the k equal to 0, 1, 2, 3, 4, and so on, n minus 1. If it is n is equal to, where capital N is equal to 9 or 10 like this, so where like the time how it is varies that a Fourier transform the periodic signal. Okay, where r and rk. This is the one way for the Fourier transform periodic. The Fourier transform of the periodic signal is like this. The inverse transform can be written as 1 by 2 pi integral, okay, 0 to 2 pi x of e power j omega. Okay, like this, the Fourier transform of the periodic signal, where so in this where 1 by where x of e power j omega is equal to what you call the summation where k equal to minus infinity to plus infinity, it's 2 pi by capital N x of k into omega minus 2 pi k by capital N. Okay, like this, where x of n is ready to calculate, ready to measure this one. So this example we will see after this. Okay, this also somewhat we will discuss later for convolution periodic impulse values. Okay. The Fourier transform of the periodic signal is how it is represented graphically. Okay, so somewhat it is the Fourier transform of the periodic. There is a relationship between finite length and periodic signal, where x of n is equal to 1 by n. From this, where x of n is equal to, before that, x of k, where x of k is equal to the summation, what you call the summation n is equal to 0 to capital N minus 1 x of n into e power minus j 2 pi by capital N into kn. Okay, so here after using this, solve the relation between finite length and periodic length signals, so where dtft, the dtft x into e power, okay, this way, and dtft, and this simplifies that x of k is equal to, finalize where x of k is equal to x of e power j 2 pi k by capital N. If it is gone substituting that k value, where k equals, since the k equal to 0, 1, 2, 3 and so on, n minus 1. Okay, where x of e power j omega, it's like it is where omega equal to 2 pi k by capital N. 2 pi, where omega, we know that since that omega is equal to what do you call 2 pi k by capital N. Okay, that N is, say for example, where this, since that N is equal to 8, according to this N value, go and substitute that k is, and so on. Okay, the Fourier transform of one period x of n. Okay, like this. This is a relationship between finite length and periodic signal. Somewhat it is verification. If x of n is periodic, with periodic capital N, the DFS are x of k. X of k is equal to the summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi by capital N into kn. If x of n is one period of x of n, that is where x of n is equal to, where that x of n, x of k, we know that where x of k is the DFT, where x of n is the IDFT, that x of n, if it is that x of n is equal to x of n is equal to x of n 0 less than or equal to n less than or equal to that n minus 1. Okay, 0 otherwise. Okay, like this. Then the x of e power j omega is equal to the summation n is equal to 0 to n minus 1 x of n e power minus j omega n, where omega value we know that. Okay, so here we are to verify that first equation, second equation are nothing but that w equal to pi k by n, that fiddle factor. Okay, this is this example we will see that after using some numerical values how it is varies. We will discuss in detail with this relationship between DFS and coefficients and Fourier like this in graphically. We are to verify. Okay, these are all are somewhat like the relationship between DFS with the Fourier transform. Okay, how it is varies. Okay, the Fourier transform and the sampling the Fourier transform and a periodic signal x of n at the d in discrete time Fourier transform x of e power j omega. If it is length m may be infinity. Okay, so what happens? Assume the sequence x of k is obtained by where if it is gone using this x of n apply with this what you call discrete time Fourier transform. Discrete time Fourier transform. You will expect that all x of e power j omega. If it is x of k, okay, if x of k is obtained by sampling with this x into e power j omega at frequency omega k is equal to 2 pi k by capital N. Okay, like this, where x of k value, that value is what you call x of k is equal to x of e power j omega at omega equal to 2 pi by capital N into k. Okay, now the sampling the Fourier transform as a periodic sequence x of n with the length m may be infinity. Okay, x of z where z is equal to e power j 2 pi by n into k, like this. So unit circle, you know, real part and imaginary part, and z plane. This length is 2 pi by n and period is n. What happened? The m and n may not be in the same. We have to consider this all points sampling frequency Fourier transform. Okay, if x of k could be Fourier series coefficients of the periodic sequence x of n with period capital N. So you can consider if it is one period, the relation is same or different. We have to prove. That purpose we are using the sampling Fourier transform and a periodic sequence x of n. Okay, the sampling Fourier transform to recover x of n. How it is recovered the x of n, where x of e power j omega is equal to the summation what you call small m is equal to minus infinity to plus infinity. Okay, x of m into e power minus j omega m. Okay, then consider this order where x of n. Okay, so after that we are to verify that x of k, where x of k we know that where x of k is what do you call where x of k is equal to x of what do you call x of e power j of 2 pi by capital N into k. Okay, so after using this all R, where we are to verify that x of e power j omega is equal to the summation. Okay, where small m is equal to infinity to minus infinity to plus infinity x of m into e power minus j omega m into to verify that x of n. Okay, now the DFS, how it is reflected the DFS. The DFS, okay, the DFS is what you call where DFS x of n is equal to 1 by n summation k equal to 0 to n minus 1 x of k, where it is, we know that it is nothing but what you call DFT, discrete Fourier transform. Okay, so it is applied x of x dash of n is equal to x of n 0, that interval 0 less than or equal to n less than or equal to n minus 1, 0 elsewhere. Okay, now after that, so it will begin with this x of k, where x of n is equal to, now it changes that 1 by n, where it is 1 by n, that x of, what you call x of n, where x of n is equal to what you call 1 by capital N, that summation, the summation where k equal to 0 to n minus 1. Okay, with that summation, okay, that small m is equal to minus infinity to what you call plus infinity, where x of m, into e power minus j 2 pi by capital N into k into m, km, with this into e power j 2 pi by capital N into kn. Okay, like this, the x of n value is utility. This is all nothing but what we call x of n. Okay, so like this, you try to verify the sampling of the Fourier transform to recover x of n. Go on using this step, this all step by step, and how many endpoints x of n, if n is equal to what you call, if it is capital N is equal to, here it is assigned where n is equal to 0, 1, 2, 3, 4 up to 8, 9, 10, 11 up to 12 and so on, how it is appeared x of, where n versus what you call x of n, n versus x of n, if it is n is equal to 12, capital N is 12, so graphically we have to verify that all, sampling the Fourier transform to recover x of n. Okay, like this, if x of n with n equal to 12, okay, where n is equal to 7, like this, okay, we have to verify. If the n samples of DTFT, Fourier coefficients of the periodic sequence is x of n. Okay, to obtain through what do you call this, discrete Fourier transform. So there is somewhat a derivation of the discrete Fourier transform, relationship between x and e power j omega and x of k in recovering x of n, based on here the length m x of n, x into e power j omega, the sampling x of n, length m. Okay, with this, after that, we have to verify that x of k, where x of k is discrete time Fourier transform. After that, so inverse discrete Fourier transform x of n. Finally, the length m is x of n. It is not necessary to know the discrete time Fourier transform and x into e power j omega at all frequencies to recover what you call x of n. Okay, with this, x of n with the x of n with the x of k. So we have to verify when the Fourier series is used in this way to represent finite length sequences, it is called the discrete Fourier transform, or you can consider that it is nothing but what we call DFT, discrete Fourier transform. Okay. So the Fourier representation finite duration sequence, discrete Fourier transform, consider the finite length sequence x of n of length n samples such that n sample such that x of n is equal to 0, outside the range 0 less than or equal to n less than or equal to n minus 1. Okay, you can consider here n versus x of n. Okay, to each finite length sequence of length n, we can associate a periodic sequence x of n is equal to the summation r equal to minus infinity to plus infinity. Here based on this, where x of n is equal to, how it is appeared, the summation where r is equal to minus infinity to plus infinity x of n minus r into capital N. Okay, use this interval minus infinity less than n less than plus infinity. Okay, this time. So the samples, therefore we represent the finite duration sequence is like this with the discrete Fourier transform. A finite length sequence x of n of the length n samples such that x of n equal to 0 outside the range 0 less than or equal to n less than or equal to n minus 1, where x of n is like this. Okay, like this we are going to verify that interval. Next, the discrete Fourier transform x of n is equal to x of n mod n is equal to x of n and n. Okay, DFS coefficients of the x of n is x of k with period capital N. With this, we try to assume that where x of k is equal to x of k 0 less than or equal to k less than or equal to n minus 1, 0 otherwise. With this, x of k is equal to that that x of k is equal to we know that discrete Fourier transform x of k is equal to the summation where n is equal to 0 to n minus 1 x of n. Okay, so with reference to this, where x of k is equal to x of k mod n is equal to x of k n, so that interval minus infinity to less than or k less than infinity. The x of k is equal to x of k, that interval 0 less than or equal to k less than or equal to n minus 1, 0 otherwise. Okay, with this we can consider DFT, discrete Fourier transform. After it is called the discrete Fourier transform of x of n. So like that we are right to assign that the discrete Fourier transform of x of n. Okay, the discrete Fourier transform, if DFS x of k is equal to, in terms of this twiddle factor, how it is varies the DFS, where x of k, okay, where x of k is equal to the summation where n is equal to 0 to n minus 1 x of n into the twiddle factor with this into e power minus j 2 pi n k by capital N. Okay, where it is, this is all nothing but the twiddle factor. This is going to be the WNK. You can consider this is WNKN. This is your twiddle factor. With this, where DFT, the DFT discrete Fourier transform, the discrete time Fourier transform x of k is equal to x of k, that interval 0 less than or equal to k less than or equal to n minus 1, 0 otherwise, where x of k is equal to This is nothing but DFT, discrete Fourier transform, where it is nothing but what you call IDFT, inverse discrete Fourier transform, where x of n is equal to x of n, that interval 0 less than or equal to n less than or equal to n minus 1. Compare this DFT and IDFT. Easily can distinguish this where what you call DFT versus IDFT, inverse discrete Fourier transform. This is nothing but what you call DFT, discrete Fourier transform. This one is inverse discrete Fourier transform. But this case is they are using this interval is what you call 0 less than or equal to k less than or equal to n minus 1. Where this case, the inverse discrete Fourier transform, we have to use this interval 0 less than or equal to n less than or equal to n minus 1. Okay, like this. Using this all up, how to represent, how they are representing this. Okay, like where x of n, this x of n, and where this x of n. Okay, so how it is, where is next? This is all nothing but what you call x of k, where x of k is what you call, it is one of the x of n as what you call this. This is IDFT, inverse discrete Fourier transform. After measuring this inverse discrete Fourier transform, there is x of k. It's also involved here. Okay, so now usually DFT, discrete Fourier transform, is written as analysis equation. Written as that analysis equation is nothing but we can consider this analysis equation where DFT, the discrete Fourier transform, is equal to x of k is equal to what you call, can consider that the summation where n is equal to 0 to n minus 1, x of n into e power minus j 2 pi n by what you call capital N into k or nk. Okay, in place of that we have to use that on fiddle factor. Okay, so like this. Okay, now usually the discrete Fourier transform is written as analysis equation. It is followed by x of k, that x of k is equal to the summation n is equal to 0 to n minus 1, capital N minus 1, that x of k, x of n is, it is trivial factor wnk, where nk, click on this and this trivial factor e power minus j 2 pi what do you call 2 pi nk by what do you call that capital N. That interval, these are all nothing but this way. The interval is 0 less than or equal to k less than or equal to n minus 1. So this is the sense, what you call, if it is synthesis equation, there is going to be what you call inverse DFT. Analysis equation is a DFT. Synthesis equation is inverse discrete Fourier transform. So you can represent that DF discrete Fourier transform versus inverse discrete Fourier transform, where DFT is synthesis equation, analysis equation, where if it is IDFT, where the inverse discrete Fourier transform is what you call synthesis equation. Like here, the synthesis equation for the inverse IDFT, x of n is equal to 1 by n, the summation k equal to 0 to n minus 1, x of k into w, n minus kn. Okay, so here it is. So that means here it is plus, here it is, that fiddle factor is minus. Okay, like this, let analyze. If it is analysis equation, x of k equal to summation n is equal to 0 to n minus 1 x of n, the twiddle factor, okay, where it is w, that is, it is nothing but e power j plus j 2 pi n into k by capital N, 0 less than or equal to k less than or equal to n minus 1. Synthesis equation where x of n is equal to 1 by n, the summation k equal to 0 to n minus 1 x of k into the twiddle factor. So w of n kn. That means here this twiddle factor, where here it is, okay, e power minus j 2 pi n k by capital N. Okay. Now where x of n applied with the DFT, where we have to verify that what do you call x of k. So this is the recall the difference transform between these two domains. Here it is Fourier. If it is using this all in terms of the domain, okay. If you are in the domain frequency, what do you call Fourier transform, the time is continuous. The Fourier transform in the frequency is continuous. Okay, frequency domain. If you are in the Fourier series in time domain is continuous periodic. It is continuous periodic. Fourier series in frequency domain discrete. Next, in discrete time Fourier transform in the time domain is discrete. Okay, but in using the DFT discrete Fourier transform, the frequency domain is continuous periodic. Now coming to the DFS, discrete Fourier series DFS. So here it is discrete and the time domain discrete periodic. If it is in frequency domain discrete and periodic. Coming to our case, so in a DFT discrete Fourier transform, okay, DFT, this on time domain is discrete finite. In the frequency domain, discrete finite only. This is we have to recollect this all different transforms between the time and frequency domains. Okay, like this, we have to verify this is the background of what you call in terms of the DFT discrete Fourier transform.
Like, share and subscribe. Hit the bell icon for more updates.